All right, let's dive right in. Today, we're cracking the code on two of the most fundamental concepts in all of chemistry, acids and bases. And believe it or not, this is a world that's all around us, probably even hiding under your kitchen sink. Take a look at this. It's a pretty familiar sight, right? You've got your drain cleaner, your oven cleaner, maybe some toilet bowl cleaner. We use these things all the time because, well, they work. But have you ever stopped to wonder what actually makes them so powerful? And that is the big question, isn't it? What is it about these liquids that lets them just obliterate grease and grime? Well, the answer is chemistry, and we're about to break it all down. So that's where we'll start. In our first section, we're going to peel back the labels on these everyday products and really discover the invisible world of acids and bases that's doing all the heavy lifting for us.
But before we can truly understand what makes an acid or a base, we have to start smaller. We need to meet their fundamental building blocks, these tiny little charged particles called ions.
So what in the world is an ion? It's really simple. It's just an atom, or even a whole group of atoms, that's either gained or lost an electron. And because of that, it now has a net electrical charge. This charge is everything. It can be positive or it can be negative, and it's the key to this entire puzzle.
You know, ions basically come in two flavors. On the left here, you see cations. These guys are positive. Think of sodium, Na+. On the right, you've got the anions, which are negatively charged, like fluoride, F-. So just remember, cations are positive, anions are negative. That's the big takeaway.
And this is where it gets kind of cool. Sometimes, a whole group of different atoms can link up and act like a single unit that has one overall charge. We call that a polyatomic ion. It's like a little team of atoms that moves around and reacts all together as one piece. This chart shows a few of the common ones you'll run into. So take a look at nitrate. That's NO3-. See that? It's one nitrogen atom and 3 oxygen atoms, all working together as a single team with a -1 charge. Or look at carbonate, CO3-2-. It's got a -2 charge. These groups pop up all the time.
Okay, so we've met the ions, now we are ready for the main event. Let's finally get to the core definition that separates an acid from a base.
The entire difference, the whole shebang, it all boils down to this one simple idea. What kind of ions do they release when you dissolve them in water? That's it. That's the secret.
And here it is. An acid is any substance that kicks out hydrogen ions, that's H+, when it's in water. A base, on the other hand, produces hydroxide ions, that's OH-. This is the fundamental difference. That H+ ion is the key player in something like toilet bowl cleaner, while the OH- ion is the powerhouse in your drain cleaner. So remember, H+ means acid, OH- means base.
All right, so now that we can tell them apart, let's learn how to speak their language. In this next section, we are going to crack the naming code for acids.
Now, you might think you need to memorize a million different names, but the secret is actually way simpler than that. You just need to look at the name of the acid's anion, that negatively charged part. The anion's name basically tells you everything you need to know to name the acid. So here are the rules. It's like a little chemistry decoder ring. First, just look at how the anion's name ends. If it ends in "ide", the acid name will start with hydro and end with "ike". If the anion ends in "ate", you just change that ending to "ic". And if it ends in "ite", you change that to "us". Let's see how this actually works. Check this out. This table lays out our rules perfectly. So the chloride anion ends in "ide", right? So it becomes hydrochloric acid. Simple. The nitrate anion ends in "ate", so it just becomes nitric acid. And the nitrite anion ends in "ite", so it becomes nitrous acid. See? Just like that, you've learned to speak the language of acids. Okay, so we can identify them, and now we can name them. There's really just one piece of the puzzle left. It's time to figure out how to write their chemical formulas, the unique signature for every single acid out there. And believe it or not, this all comes down to one golden rule. When you combine the positive H+ ions with the negative anion, the total charge of the final molecule has to be 0. The positives and the negatives have to perfectly cancel each other out. That's the entire game. Let's start with a really simple one, hydrobromic acid. Okay, so the hydrogen ion, H+, has a +1 charge, and the bromide anion, Br-, has a -1 charge.
Well, +1 and -1 equals 0, a perfect balance. So the formula is just HBr, one of each.
Okay, now let's try one that's a little trickier. Sulfurous acid. Now the sulfide ion has a -2 charge. So one little H+ ion with its +1 charge, that's just not going to be enough to balance things out. So what do? We need 2 of them. 2 H+ ions give us a total charge of +2, which perfectly balances the -2 from the sulfide. And that is exactly why the formula is H2SO3.
Let's do just one more to really lock this concept in. Phosphoric acid. Okay, the phosphate anion has a pretty big -3 charge. So, how many H+ ions are we going to need to balance it out? You got it, 3. 3 H+ ions give us a +3 charge, which balances that -3 perfectly, bringing us to 0. And the formula is H3PO4. Look at that, you're building molecules.
So let's do a super quick recap. We learned that ions are just charged particles, positive cations and negative anions. We learned the absolute crucial difference between acids and bases. Acids make H+ ions in water. Bases make OH- ions. We totally cracked the code for naming acids just by looking at their anion. And we mastered the golden rule for writing chemical formulas. Always, always balance the charges to 0.
You know, we started this whole thing just by looking at a bottle of cleaning spray, and now you can actually read and write the chemical language of what's inside it. You've cracked the code. So the only question left is, with this new knowledge, what are you going to choose to understand next?